In the last lesson on mass percent composition, we discussed how to calculate the mass percent composition of a compound from a chemical formula. So the question now is, can we do the opposite? That is, can we calculate the chemical formula by knowing the mass percent composition of the compound? So let's see what Roadkill the lab rat has to say in answer to our question. He says, indeed we can. That is, yes, we can calculate the chemical formula of a compound from knowledge of its percent composition. So let's start by taking a look at what we're going to be trying to accomplish in this lesson. First of all, it turns out that there are two types of chemical formulas, what we call empirical formulas and molecular formulas. So we need to understand the definitions of each and be able to distinguish between them. Once we've done that, we will talk about how to determine the empirical formula of a compound given either the mass of each element in a sample of the compound, that's something that can be determined from experiment, or, as we were saying previously, by knowledge of the mass percent composition of the compound. Once the empirical formula of the compound is determined, the next step would be to determine the molecular formula of the compound, once that empirical formula is known. So let's start by taking a look at the definition of both an empirical formula and a molecular formula. An empirical formula is a chemical formula giving the lowest whole number ratio of each type of atom in a compound. Now, the empirical formula may or may not represent the true number of each type of atom in the smallest unit of the compound. It turns out that since ionic compounds don't form discrete molecules, ionic compounds can only be described by their empirical formulas. That is the simplest whole number ratio of each type of atom in one formula unit. Remember, a formula unit is the smallest unit of an ionic compound. Now, for compounds that involve covalent bonds that actually form discrete molecules, for those types of compounds we can talk about a molecular formula. A molecular formula is the true chemical formula representing the total number of atoms of each element present in one molecule of the compound. Now, it turns out that molecular formulas are intimately related to empirical formulas. We'll discuss two relationships that will become important when we soon talk about how to determine the molecular formula of a compound. Starting with the relationship between the empirical formula and the molecular formula, remember that the empirical formula shows the simplest whole number ratio of each type of atom in one unit of the compound. So for molecular compounds, the real number of atoms must be a whole number multiple of this simplest ratio. In other words, the real molecular formula could contain twice as many atoms of each element, or 3 times as many atoms of each element, for example, or let's say in general, n times as many atoms of each element, where n has to be a whole number multiple, like 1, 2, 3, and so on. When we multiply the subscripts of the empirical formula by this whole number n, the empirical formula becomes the molecular formula. If we can get the molecular formula by multiplying the number of each type of atom in the empirical formula by a whole number, we just said n, then it would make sense that the molar mass of the molecular formula containing the true number of atoms could be obtained by multiplying the mass of the empirical formula by the same whole number n. Now, in the next slides, we'll take a look at some examples to better understand these relationships. Now, in this first example, we're going to take a look at 2 very common industrial compounds, namely acetylene, and benzene. Acetylene is a common gas used in welding. Think about acetylene torches. While benzene is an important solvent used in the production of nylon. Both of these compounds have the same mass percent composition, each containing 92.3% carbon and 7.7% hydrogen by mass. We're asked to first determine the empirical formula of each compound, and secondly, to show that the molecular formula of each compound obeys the relationship stated in the previous slide between empirical and molecular formulas, namely that multiplying the subscripts of the empirical formula by some whole number n will transform the empirical formula into the molecular formula. So let's start by reviewing what we mean by an empirical formula. The empirical formula is, by definition, the chemical formula giving the lowest or smallest whole number ratio of each type of atom in the compound. So when we look at these 2 compounds and their true molecular formulas are given, when we look at the simplest whole number ratio of carbon to hydrogen in each compound, starting with acetylene here, we see that in 1 molecule of acetylene we have 2 carbon atoms and 2 hydrogen atoms, so that carbon to hydrogen ratio is 2 to 2, which in simplest form is a 1 to 1 ratio. When we look at benzene, in 1 molecule of benzene, the carbon to hydrogen ratio, we've got 6 carbon atoms and 6 hydrogen atoms. Once again, taking that simplest whole number ratio, 6 to 6, goes to 1 to 1. So what we see is that although each of these compounds contain different numbers of carbon and hydrogen atoms in 1 molecule, we see that the ratio of carbon to hydrogen is exactly the same in both of these compounds. In other words, their empirical formula, which is given by the simplest whole number ratio, a 1 to 1 carbon to hydrogen ratio, is exactly the same for both compounds. So we can write the empirical formula. We don't need to write those subscripts 1, C1H1. We can simply write as CH. That is the empirical formula, showing the simplest whole number ratio of each type of atom in the compound. Now, the molecular formula, as we said, must be a whole number multiple n of the empirical formula. We can state it by saying the molecular formula is the empirical formula, where the subscripts are going to be multiplied by that number n. So starting with acetylene, we see here that the empirical formula given by CH, when we multiply those subscripts by the whole number 2, when n has a value of 2, the empirical formula C1H1, okay, multiplied by that subscript 2 gives us the true molecular formula C2H2 for acetylene. For benzene, it turns out that the empirical formula C1H1 multiplied by the whole number n equals 6 gives us the true molecular formula C6H6 for benzene. So we see then that multiplying the subscripts of the empirical formula by a whole number, okay, 2 for the case of acetylene and 6 for the case of benzene, will transform an empirical formula into a molecular formula. All right, so in the last problem, you recall, we were given two compounds, okay, where the molecular formula for each of those compounds was given to us. And from that molecular formula, we were asked to determine the empirical formula of each compound. That is the simplest whole number ratio of each type of atom in that compound. In this problem, we're asked to do the opposite. In this problem, we are also looking at two compounds, okay, formaldehyde and acetic acid. And in this problem, we're given the empirical formula, okay, CH2O, as well as the molar mass of each of these compounds. So given the empirical formula of each compound and the molar mass of each compound, we are then asked to determine the molecular formula of each compound. So we're going to start by finding the molar mass of the empirical formula. Remember, each of these compounds shares the same empirical formula, CH2O. So as we've done many times, okay, CH2O, if we take a look at the molar mass, that is the mass of 1 mole of carbon atoms, okay, 2 moles of hydrogen atoms, and 1 mole of oxygen atoms, we will get the total mass of 1 mole of, okay, this compound here, okay, at least the empirical formula of it. So do the number crunching, we get about 30.03 grams per mole. Remember, we stated these two important relationships. We know that the molar mass of the molecular formula is a whole number multiple of the molar mass of the empirical formula. Okay, in other words, the molar mass of the molecular formula must be equal to the molar mass of the empirical formula times a whole number n. Okay, in this case, we're going to need to figure out n. So for formaldehyde, okay, the molar mass of the molecular formula is given to us in the problem, 30.03 grams. We figured out the molar mass of the empirical formula, which is also 30.03 grams. Okay, so we see that for formaldehyde, the value of n must be 1. Okay, it looks like the true molar mass of formaldehyde is the same as the empirical formula mass, okay, in which case n equals 1. Therefore, the molecular formula for formaldehyde is exactly the same as the empirical formula, namely CH2O. When we look at our other compound, acetic acid, looking at the same relationship, okay, that the molar mass for the molecular formula must be a whole number multiple n of the molar mass of the empirical formula, substituting in our numbers, okay, the 60.05 grams per mole, that's the molar mass of the molecular formula, which is given to us in the problem. That must equal some whole number n times the molar mass of the empirical formula, 30.03. When we divide, we discover that n has a value of 2. Okay, in other words, okay, we can now use the fact that the molecular formula, okay, must be related to the empirical formula, where the subscripts of the empirical formula are going to be multiplied by this whole number 2. So we take our empirical formula CH2O, okay, multiply those subscripts by 2. Okay, we now get the true molecular formula for this compound, C2H4O2. All right, so now that we've talked about the relationship between the empirical formula and molecular formula, as well as the relationship between the molar mass of the empirical formula and the molecular formula, we're now in a position to put this all together and talk about how to calculate the chemical formula of a compound. Okay, now remember, for ionic compounds, Okay, we can only talk about an empirical formula for them. Okay, but in the case of molecular compounds, we can take the additional step and talk about how to find the actual molecular formula once the empirical formula is known. So here's a step-by-step procedure. In this slide, we'll take a look at the steps. In the slides that follow, we'll take a look at applying these steps to various examples. Okay, so the first step is to identify the mass of each element in the compound. Now, I say here assume a definite starting quantity of the compound, okay, and express the mass of each element in the compound in grams. Now, this may be given to you in the problem. Okay, you may be given experimental data where you know the mass of each element, or you may be given mass percent composition data instead, in which case you don't know the actual masses of the elements. Okay, you simply know the ratio of each of those elements in the compound by mass. So in that case, go ahead and assume any starting quantity you want. I say here assume 100 gram starting quantity because that allows you to convert a percent into grams very easily. Okay, since it's only the ratio of masses that counts, it really doesn't matter what starting quantity you use. So make your life easy, assume a simple value like 100. Okay, once you know the masses of each of the elements in your compound, okay, the second step is you have to convert those masses, okay, into moles. Remember that elements, when they come together to form compounds, they don't do so by mass, they do so by particles. Okay, so that's why we have to convert masses into particles, and of course we're going to use the unit moles to do this. Okay, once that's done, okay, we're going to have the number of moles of each of the elements in the compound. So here we're going to divide each of the value we obtain, okay, in step 2 by the smallest of the values. Okay, and we'll, in the next slides, take a look at, okay, how to actually do this. Okay, once that's done, okay, there's two possibilities. Those numbers you get when you take the number of moles of each of the elements divided by, okay, the element having the smallest number of moles. Okay, one possibility is that the numbers you obtain are going to be whole numbers, in which case your life is easy. Simply use those values as subscripts in writing the empirical formula. Okay, the more probable, the more likely result is that the numbers you obtain will not be whole numbers. Okay, in which case you then need to multiply each of them by the smallest whole number possible. Okay, so start by multiplying by 2, then by 3, then by 4, until you can convert them all into whole numbers. Then you can use these newly found whole numbers as subscripts in the empirical formula. Once again, we'll take a look at how to do this in the slides that follow. So basically, at the end of step 3, you will have an empirical formula for your compound. Now, if your compound is an ionic compound, then that's as far as we can go. Ionic compounds are only expressed in terms of their empirical formulas. But if you have a molecular compound, you can take the additional step. Okay, if the molar mass of the compound is known, then you can determine the molecular formula. Okay, and we've done this in the previous slide. So remember the relationship between the empirical and molecular formula. Okay, the molar mass of the molecular formula, okay, must be an integral number, a whole number multiple of the molar mass of the empirical formula. So dividing the molar mass of the molecular formula by the molar mass of the empirical formula gives you that whole number. Okay, and remember we showed that once you know what that whole number is, you can multiply the subscripts in your empirical formula by that whole number to get the molecular formula. All right, so let's apply this procedure to a couple of examples. So in this first example, we'll take a look at how to calculate a chemical formula from experimental mass data. So in this problem, we're told that an unknown white powder is analyzed, okay, and found to contain 109.10 grams of phosphorus and 140.90 grams of oxygen. The compound has a molar mass of 283 grams per mole. Okay, we want to find both the empirical and molecular formula of the compound. So step 1, Okay, just repeating what we had on the previous slide. Assume a definite starting quantity of the compound and express the mass of each element in the compound in grams. Now in this problem, we are actually given the mass of each of the elements in the compound in grams. So in this problem, an experiment was done, okay, in which case this compound was analyzed or separated into its elements, okay, and the mass has been given to us. So there's really nothing to do here, okay, just record the numbers. The second step is to take the masses of each of those elements and convert them into moles. Okay, and we do that by using the molar mass as a conversion factor. So starting with phosphorus, the 109.10 grams of phosphorus, okay, we're going to arrange the molar mass. We're going to divide through by the molar mass here. Okay, notice that we cancel out our unwanted units of grams and end up with units of moles of phosphorus. Okay, we will do the same for oxygen. Okay, we'll divide by the molar mass. Okay, once again canceling out our unwanted units of grams, being left with units of moles. So now we've effectively converted the mass of each element into the moles or number of particles of each element. All right, so in step 2, we found the number of moles of each of the elements in the compound. Okay, in this step, we are now going to divide, okay, by the smallest of those values. So recall that for phosphorus, we had 3.523 moles. For oxygen, 8.806 moles. The smallest of those two numbers is the 3.523. So we're going to divide, okay, the number of moles of phosphorus, okay, by itself. That's going to give us the whole number 1. And for oxygen, the 8.806 moles of oxygen divided by the 3.523 moles, okay, for phosphorus gives us a number 2.5. Now you'll notice that the number 2.5 is not a whole number. Okay, so we need to take this additional step. We are going to multiply both of those numbers by the smallest whole number that will convert them into whole numbers. So starting with the smallest whole number other than 1, it would be 2. You'll notice that when we multiply 1 by 2, we get the number 2, which is a whole number. When we multiply 2.5 by 2, we get the number 5, which is a whole number. So it looks like multiplying by the smallest whole number 2, okay, will produce the whole numbers 2 and 5. So we are now ready to write down our empirical formula. This tells us the ratio of phosphorus to oxygen in the compound, okay, by particles. So that tells us that for every 2 particles, 2 atoms of phosphorus, we're going to need 5 atoms of oxygen, okay, in that smallest unit. Okay, now since this is a molecular compound and the molar mass of the molecular compound is given, we can take this additional step to find the molecular formula. The empirical formula is P2O5. Okay, so remember this relationship we talked about previously, that the molar mass of the empirical formula, okay, is related to the molar mass of the molecular formula. Okay, in other words, the molar mass of the molecular formula must be an integral number, a whole number multiple of the molar mass of the empirical formula. So we can find out what that whole number multiple n is by dividing the two. The molar mass of the molecular formula is given to us in the problem. It's 283 grams per mole. We need to calculate the molar mass of the empirical formula that we just found in step 3 for P2O5. So when we add the 2 moles of the phosphorus atoms plus the 5 moles of the oxygen atoms, that gives us okay, the molar mass of the empirical formula to be 141.94. When we divide these two, we see that we get the whole number 2. That tells us that, okay, we can multiply the subscripts in our empirical formula by 2 to come up with the molecular formula. That will transform our empirical formula into a molecular formula. So P2O5, Okay, multiplying each of those subscripts by 2 gives us P4O10. So we've now found the true molecular formula of this compound. All right, so let's take a look at one last example. And in this example, we'll look at how to calculate a chemical formula from mass percent composition data. So in our problem, we're asked to determine the empirical and molecular formulas of a compound that contains 71.65% chlorine, 24.27% carbon, and 4.07% hydrogen if the molar mass of the compound is known to be 98.96 grams per mole. So step one, now recall in the last problem we were given the actual masses of each of the elements in our sample, right? Some experiment had been done in which the masses of each of the elements were determined through some sort of separation technique. In this problem, we're given mass percent composition data. So we don't know the actual masses of the elements, but since it's only the ratio of masses of each of the elements that counts, it doesn't matter. So here's a case where we can assume any quantity, any size sample of the compound we want, so long as we get the ratio of the masses right. So as I was saying previously, make your life easy. Let's look at a 100 gram starting quantity, in which case when we convert percents, mass percents, into actual grams, we do not need to change the numbers. So in this case here, 71.65% chlorine by mass in a 100 gram sample gives you 71.65 grams of chlorine in that sample. And for carbon, the 24.27% carbon by mass translates into 24.27 grams of carbon in a 100 gram sample, and likewise for hydrogen, the 4.07% becomes 4.0 grams. So we've made up a sample. Okay, we have masses of each of the elements in our made up sample. We're now ready to convert those masses into moles, okay, using the molar mass of each of the elements. So for chlorine, okay, we can divide by the molar mass and we end up with 2.021 moles of chlorine. Okay, for carbon, our 24.27 grams of carbon becomes 2.021 moles of carbon. And for hydrogen, our 4.07 grams of hydrogen becomes 4.03 moles of hydrogen. All right, so now that we know the number of moles of each of the elements in the compound, okay, we take the next step, which is to divide each of those number of moles, okay, by the smallest number of moles. So when we look at our number of moles for each of the elements, remember chlorine had 2.021, carbon 2.021, hydrogen 4.03. So the smallest number would be, okay, that for carbon and chlorine of 2.021. So we divide each of the number of moles by the smallest number of moles of 2.021. That gives us, for chlorine, the number 1, for carbon, the number 1, and for hydrogen, the 4.03 divided by the 2.021 gives us the number 1.99, which experimentally is close enough to 2. That's close enough to a whole number. So in this problem, okay, the answers we get when we divide each of the number of moles, okay, for our elements by the smallest number, we end up with whole numbers. So we do not need to take this additional step. Okay, we are now ready to write down the empirical formula. Remember that once we have whole numbers, okay, then we can use those numbers as subscripts in the empirical formula. So this tells us that, okay, for every 1 atom of carbon, okay, we will have 2 atoms of hydrogen and 1 atom of chlorine in our smallest unit of that compound, our empirical, okay, formula unit. So we now have the empirical formula. The next step, okay, is to determine the actual molecular formula, if we know the molar mass, which in this case we do, is 98.96 grams per mole. So let's take this additional step here. Remember that the molar mass of the molecular formula must be a whole number multiple of the molar mass of the empirical formula, which tells us that by dividing the molar mass of the molecular formula by that of the empirical formula, we will get that whole number. Okay, the molar mass of the molecular formula is given to us in the problem. Now that we know the empirical formula from step 3, we can figure out the molar mass, okay, which requires us to add the molar mass of each of the elements in the compound. So for 1 mole of carbon atoms, we're going to add the 12.01 grams, and okay, we have 2 moles of hydrogen atoms at 1.01 grams and 1 mole of chlorine atoms at 35.45 grams. We add it all together for an empirical formula mass of 49.48 grams. When we divide these two, we get the whole number, as we must, of 2. That tells us then that if we multiply the subscripts of our empirical formula by this whole number 2, we will transform our empirical formula into a molecular formula. So the CH2Cl2 multiplied by the subscript 2 gives us the real molecular formula of C2H4Cl2. This is the compound known as dichloroethane, okay, a widely used industrial solvent that is used in the manufacture of polyvinyl chloride, more commonly known to us as PVC.